Hi, this is going to be a discussion that relates to a demonstration that we're going to be involved in. It's something called the International Boiling Point Project. Our school is going to participate with other schools in different parts of the world in this project. We're going to input data into an Excel spreadsheet that relates to the boiling point of water at our elevation where we are located right now at our school. So we'll know our longitude, our latitude, and our elevation from Google Earth, and we'll proceed with the protocol on the web link for this project. Briefly mention a couple of the things that are involved. We're going to use distilled water. We're going to measure 100 milliliters of water. We're going to boil that water with a Bunsen burner or a hot plate. Okay, we're going to take your temperature reading every 30 seconds for 5 minutes until those big bubbles start to rise to the surface and we know the water is boiling. That's the definition of boiling. We'll talk more about that, but that's kind of where some of the protocol for this experiment is going to be controlled. We do it for 3 different days. We're going to take averages over those 3 days, and we're going to do some input this data on the spreadsheet and analyze it and graph it. Right now, though, I'd like to introduce the subject a little bit more and get you thinking a little bit about boiling and vapor pressure and things sometimes we might not think about every day. So I'll run through a few things that we already know or things that we should know before we start this experiment, this demonstration. First, I'll just go through them very quickly. When water is heated to 100 degrees centigrade in an open container, it boils. So boiling is a special case of vaporization. Okay, vapor pressure is a physical property of liquids. Vapor pressure is the pressure exerted by a vapor in its liquid form. It's the pressure coming up and out of the vapor, the liquid, I should say, any liquid, water or any liquid, and there's pressure coming down, of course, atmospheric pressure too. So boiling is when water is heated to the point where vapor pressure, which is pushing up, equals the atmospheric pressure that's pushing down, and the molecules kind of spontaneously vaporize in a process called boiling. Okay, in order to vaporize, molecules must gain enough energy from their environment to overcome the intermolecular forces that keep them bound to the liquid phase. So I think we know all that from previous lessons. Liquids and water will not boil if they are at temperatures where their vapor pressure is less than the atmospheric pressure. Okay, then water does not boil in that case. And we also know temperature is a measure of the average kinetic energy of molecules. So that's the kind of stuff we already know. And I'd like to get you to start thinking about some questions that will relate to this demonstration. But before I do, I'll just mention one thing that I think is kind of interesting, is that about 20 kilometers above the Earth's surface, about 12 miles above the Earth's surface, the atmospheric pressure equals the vapor pressure of the human body. The vapor pressure of the human body is about 47 milliliters of mercury. So at that pressure, or that altitude, the bodily fluids in the human body start to boil. And actually, seems kind of a bizarre thing that you don't think about very often, but that kind of puts things in a little bit of perspective. So there's a number of questions I just want to throw out and have you think about before we do this demonstration. One is, how does elevation influence the temperature at which liquids boil, or the amount of time required to cook foods? Can water that's near its freezing point, that's fairly cold, can it actually boil? Can water near its freezing point boil? What would happen if you added salt to boiling water? Right? What would happen to the molecules? What would happen to the boiling point? What happens to the boiling point of water when we put a lid on a pot of water and then boil it? You got a closed system or an open system. What happens in each case? Why do we have to cook food longer at higher elevations before you can eat it? When cooking in an uncovered pot, why doesn't the temperature rise above 100 degrees centigrade? How do pressure cookers work? When we put a top on a pot, we have a closed system. What will the increased pressure do to the boiling point? When water is heated, it boils because energy has been added. But how does that mean? What does that mean if we have water sitting in a puddle or a cup on a desk and it evaporates? Where is the energy coming from in that case to evaporate the water if we don't have a fire or flame underneath it? How does sweating influence body temperature? Why do doctors recommend that you dampen your skin with a cool cloth when you have a high fever? And interestingly, think about this one. If you're on Mars, where the atmospheric pressure is about 6.1 millibars compared to, say, 1,000 millibars on Earth, what does that mean for the existence of water? So there's very little pressure. So could water exist? If it did exist, what would happen to it? So we have all these variables. We have atmospheric pressure, temperature, and these things that affect water in the boiling point, not just water, but any liquid. And they're really important physical characteristics of liquids that we'll be looking at in this experiment. So anyway, that's some background, and hopefully we'll get into the experiment and learn a lot more as we go along. Thank you.